Welcome to the Bodhi Academy. My name is Ansha Klaso, and in today's video we will continue with our chapter Solutions, class 12, chapter 1. So in today's class we are going to talk about vapor pressure of liquid solutions. Okay, so now when we say liquids, we mean that we are considering the solvent to be the main liquid plus the solute that is present in that solution. It can be anything, it can be gas, it can be a solid, or it can be a liquid. So these together, that is the solvent, that is the liquid, along with any solute, any state of matter that is present as the solute is together known as the liquid. Now in this video we will discuss the properties of only binary solutions, that is the solutions containing two components, namely the solutions of liquids in liquids wherein the solvent is also liquid and the solute is also liquid, and secondly we will talk the same properties for solids in liquid where solute is the solid and solvent is the liquid. Now when we talk about binary solution, let's take an example. Say we have a binary solution that has two volatile gases, volatile liquids, sorry. In that two volatile liquids, say we have component 1 and component 2. Now both of these volatile liquids, they are packed into a closed vessel. Now eventually what would happen, because they are volatile, they are going to get evaporated off and a equilibrium between the liquid and the vapor phase will be established. Now so if we have to find the total vapor pressure, we will write it as P total, and the vapor pressure of both the components can be written as P1 and P2 respectively. So now giving a relation of mole fraction, we can write for both the components, we'll write x1 and x2. Now there was a scientist named as Francisco Marté-Raoult who gave this Raoult's law, which gave a direct relation between the mole fraction and the vapor pressure of the liquid. So he said that, or his law stated that, for a solution of volatile liquid, so we are only talking about volatile liquids here, the partial vapor pressure of each component of the solution is directly proportional to the mole fraction that is present in the solution. So vapor pressure of each component is directly proportional to the mole fraction that is of each component present in the solution. So what we can say is that, say for component 1, we can say that P1, that is the vapor pressure, is directly proportional to x1, that is the mole fraction, and P1 equals to P01 into x1, where P01 is the vapor pressure of the pure component. Similar way we can write down an equation for the second component. Now according to Dalton's law of partial pressure, the total pressure is said to be the sum of the partial pressures of the components of the solution, and that can be given as P total equals to P1 plus P2. Now P1 we have already derived here, it is P01 into x1, and P2 is P02 into x2. Now if we look at this x1 here, if I have to find, we know mole fraction is always going to be less than 1. Okay, so in that case if I do 1 minus x2, I will basically get x1 value. So I have just splitted this x1 into this form. So in that case I'll write 1 minus x2 bracket P01 plus P02 dot x2. Only this part x1 I have split it into 1 minus x2. Now I will open up this bracket by multiplying this P01 to both. So I'll get P01 plus P01 x2 plus P02 into x2, that is the remaining term. So now here we have x2 terms that are common. So what I'll do, P01 plus what is common, x2, I take it out, and rest what is remaining is P01 minus P02. So that gives us the total vapor pressure of the solution. Now from this above we can draw a few conclusions. So first is that total vapor pressure over the solution can be related to the mole fraction of any one component. Okay, so the total vapor pressure here, if you see, we started with both the mole fractions, but eventually what did we end up with? We only consider one of the mole fraction of any one component. So the total vapor pressure over the solution varies linearly with the mole fraction of component 2. So they are always in a linear relation. Now depending on the vapor pressures of the pure components 1 and 2, total vapor pressure over the solution, it will decrease or increase with reference to increase in the mole fraction of component 1. Okay, now we'll see about Raoult's law as a special case of Henry's law. So we will see how is this possible. So now according to Raoult's law, we know that Pi equals to a mole fraction into the vapor pressure of the pure component, correct? Now in a solution of a gas in a liquid, one of the component is so volatile that it exists as a gas, and we have already seen that its solubility is given by Henry's law. So previous video we spoke about the Henry's law, which gave us this equation that said P equals to Kh into X, where Kh is a proportionality constant and X is the mole fraction. Now on comparison of both the laws, that is Henry's law and Raoult's law, what we can see is that the partial pressure of the volatile components, it is directly proportional to the mole fraction. Here also we are having this x1 and here also we are having this x. So in both cases the mole fraction is directly proportional to the volatile component. So only what is differing in both cases is the proportionality constant, that is Kh from P0 1. So what we can say here is that this Raoult's law is a special case of Henry's law only, wherein this Kh is equal to P0 I in this cases. Okay, so that was about the Raoult's law as a special case of Henry's law, because both of them are stating the same thing, that the volatile components are directly proportional to the mole fraction of the solution. Now in that case, the only thing that is differing is the proportionality constant that are present. The Henry's law has the Kh and the Raoult's law has P0 I. So in that case, what we can say that Kh and P0 I are equal when it comes to a special case of comparing Raoult's law and Henry's law. Now let's talk about the vapor pressure of solids, vapor pressure of solution of solids in liquids. So liquids at a given temperature vaporize, and under equilibrium conditions the pressure exerted by the vapors of the liquid over the liquid phase is called as the vapor pressure. So what they are saying, at a certain temperature what will happen, the liquid, they will start to vaporize, and after the equilibrium conditions are attained, over then the pressure that will be exerted by the vapors on top of the liquid phase, okay, that is called as the vapor pressure. Now in a pure liquid, the entire phase is occupied by molecules of the liquid. So when we say pure liquid, that a solvent is only liquid. So if a non-volatile solute is added to the solvent to give a solution, the vapor pressure of the solution is solely from the solvent alone. So now if you have a liquid, to that you are adding a non-volatile solute. So in that case also what will happen, the vapor pressure is only dependent on what, the solvent, that is the liquid. Why? Because we consider only volatile solutes over here. In now this case what we have done, we have added a non-volatile solute which won't go into the vapor phase. So therefore what will happen, only the liquid will go, that is the solvent will go into the vapor phase, and the vapor pressure of the same will be considered. This vapor pressure of the solution at a given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature. So now they are saying that the vapor pressure of this solution after adding the solute is said to be much lower than the vapor pressure of the plain solvent that was initially there. Now in the solution, the surface has both solute and solvent molecules. Thereby the fraction of the surface covered by the solvent molecules get reduced. So what they are saying, in the solution what we have both. The surface has both the solute molecules, the non-volatile solute and the solvent molecules. Hereby what will happen, the fraction of the surface that is covered by the solvent molecules, it will get reduced. Consequently, the number of solvent molecules escaping from surface is correspondingly reduced. Thus the overall vapor pressure is also reduced. So now Raoult's law in general form can be stated for any solution. The partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. So what we are saying, in general we are making a statement that for any solution, the partial vapor pressure that is there of each volatile component in the solution, it will always be directly proportional to its mole fraction. Now let's understand this. In a binary solution, now let us denote the solvent. Let us consider an example of a binary solution. So in that, let us denote the solvent by 1 and the solute by 2. So when the solute is non-volatile, okay, only the solvent molecules are present in vapor phase and they contribute to the vapor pressure. So therefore, let P1 be the vapor pressure of the solvent and X1 be its mole fraction, and P naught I be the vapor pressure in the pure state. So then according to Raoult's law, we can write that P1 is directly proportional to X1, and therefore P1 will be equal to X1, that is the mole fraction, and P naught 1, that is the vapor pressure in the pure state. So therefore the proportionality constant is equal to the vapor pressure of the pure solvent, that is P naught 1. Okay, so now the plot, when you plot it against vapor pressure and mole fraction of the solvent, what you see is that you get a linear graph. So a plot between a vapor pressure and the mole fraction of the solvent is linear. Why? Because they are directly proportional. If one is increasing, the other one will also increase. Okay, so if a solution obeys the Raoult's law for all concentration, its vapor pressure would vary linearly from 0 to the vapor pressure of the pure solvent. So it will straightly go from 0 to the vapor pressure of the pure solvent. Okay, so that was it for today's video. I hope you have understood. Please don't forget to like, share and subscribe to the Bodhi Academy.